Hello. It's fine now. Thank you. Sorry. The HDMI 有办法哦，它东西长这样，真是天才。下次要再 test 一个东西，好像是要拆了过后才可以开，才会 work。
可以这样的。
我猜了，每次都是这样的，它才 work，不然的话它就死都不要开给我看。你要，你不要写东西啊，还是你要
写来吧，
？OK，可以。
写东西应该是补充罢了。
可以。我要学 share 是吧？应该学的。
你这么没有啊？
啊？
没有。
哦哦，等一下，你要拿过去，拿过去。嗯，可是就不是 sharing screen 了，有想下这样做，maybe duplicate 它。还好吧？应该这样。还是就是感觉这个，对啊，这个情况。还有那个自由地方，自由跟原力跟个反射力。还有一本书哦，他那个去那个因为走来去了是回很多，我们也
我们不是可以接
难看。就问老师那种啊，就问老师那时候所有 seven 是写 read extension 吗？read extension，所以他的我跳动来的一种是全部东西就说一些。
？OK OK. Hi everyone. My name is Chuen Jack. And then today I want to discuss the idea and the quotient range. Okay. Yeah, for the chapter 3, and then section 4 is the prime idea and the maximum idea. Okay. Okay. This I will go. Okay. Next. Okay. First, we define the left, right, and two side idea. Okay. Let R be a ring, and then I, the subgroup of R for addition, and then left ideas mean if Ri in I for every R in I. Okay, and then the right idea is just IR in I. We say the two side idea is if both Ri or and IR also in I. Okay. The equivalent is same like if I have an element in the idea, and for all R in R, RA is also in I. Okay, same like R. The next very important this idea is not a subring, okay? Because not necessarily contain one the multiplicative identity. If idea it contain the multiplicative identity, then I is just R itself. Okay? If I is a subset of R, okay? If I idea contain the one, and it is R itself. Yeah, why? Because like it's a subset of R. And then if I contain in I, then every R is R of I. Every R in I. Okay. Okay. Next proposition say if phi, a map from R to S, is a ring homomorphism, then the kernel of phi is a two-side ideal. And because kernel, we send the thing is to 0, right? Then we get everything is 0, so the RA and AR also is in the ideal. Okay? That's just a very easy one. Okay, next we define the quotient group with R quotient with the ideal. What does this mean? Okay, this is equal to the set contain the R plus I for every R in R. Okay. The quotient of the ideal. Then we have the projection map R to I quotient I. We send R to I plus I. And how to define this? We do the multiplication like A plus I times B plus I equal to AB plus I. Okay. And next we will well define why.
This I have to be and by you.
That's right. It's same lah. Same. How to say this? We just do one side lah. It is same all for all lah. For left and right is like if you it's right right is it cannot left. Very big caution. Caution is a left. R plus I. Cannot because we define this one.
Yeah. So this idea is that ideal. Because it's commutative.
Yeah, ring right?
Huh?
R is ring. R is ring, then R plus I equal to I plus R. No? You know the commutative.
That one is true, but then
So
but then AL, what's AL?
AL. Sorry,
A times I.
A times I is in I.
Right.
Ideal, the definition of ideal.
Ideal, but that's right.
Yeah.
If it's right, ideal, then it might not. This one is the left one.
I think we talk all is left first. Yeah, then right, let me think can relate to this or not. We talk about the left first. Okay. These are just now theorem. Okay.
Oh, two-sided, you need two.
Yeah, two-sided. I can say like this. All of this we talk about two-sided. Or I say idea is two-sided idea. I don't specify the left or right. Okay. Okay. This same as just now, but one more thing is the identity is 1 plus I. Okay. Okay, this also only need to check well defined. Okay. if we have the two different a prime, a double prime, and b prime and b double prime. Then we want to check this is equal. Okay. Then we take the minus because the minus is also in I. Okay. So we do a trick here. We want to check this is in I. So we want to prove this is in I. Okay. So we do a trick here. We minus something and add back. Okay. And we factorize. We get this b double prime and b prime, a double prime and a prime. So this two is in I, and this a double prime, b prime, and this I is also in I. So this all thing is in I. Okay. So this is in I. So a prime b prime plus I equal to a double prime b double prime plus I. Okay. Okay. Next is quotient ring. If I is a two-side idea of R, the ring R quotient I is called the quotient ring of R modular I. So now we talk this is we say this is R mod I. Okay. And this example R Z is a ring. Okay. Z is a ring, and I is the NZ. Why this is an idea, and later we check out that. Then this is the ring congruent to the modular N. We have to check or not. No, we don't have to check. I check here. Okay. Y, Z, and Z. Yes. And these are very easy to think like because NZ is defined like every element P, not P, Z lah. Z equal to multiple of N. Sum N, F of sum N. Not sum for all. Okay. Then every element here, Z equal to N times M. Okay, for M. And then we say proof the idea is for all Z in NZ, we want to prove Z plus all here. Z want to prove it's a subgroup of Z. Want to prove subset. I will prove this up plus times. Okay, because this I can write maybe like K M M. Then this also can write like A times like this. Also in Z, NZ. Okay, so this idea. And then left also same. This is a right, this is a left. Okay. Left, right. Okay. Idea.
For some
For some
the calculator of that.
oh this Oh. M is unique.
Set 0, but then for the rest of
Zero. Zero also can be zero also in
and
Z.
if you have M inside and Z,
Okay.
then M should be just equal to 1. That's completely.
M is the N is 2. I choose M is 1, 2, 3 also can, then 2, 4, 6. Also yeah.
I thought you say that you want to write Z in terms of program. I think it should be unique.
Unique.
Or Z not equal to 0.
And everything unique or Z not equal to 0.
Not equal to
What to say unique? Just you mean
Z.
okay, choose 2Z. Then Z before.
Look at 4 exactly.
Okay. Oh, you mean 4 is equal to 2 times 2, and then this M is unique. Okay. I get it. Okay. Oh, so you mean this is unique, so we don't use the or lah. For all, use the S is. Oh, okay. Okay, thank you. Okay. For characteristic of a ring, since Z is an initial in a ring, then we have a unique ring homomorphism like this. We define M sent to the M times 1. This means we add the 1, identity 1, M time. Okay. Then the kernel is an idea of Z. Okay, so we
Better you write that down.
this definitely. Yeah. Okay.
Mean not now. Not now we know.
The one.
We are not.
Okay. For unique N. Okay. Then the integer N is the what is the N? N is a characteristic of R. Okay. The next is a theorem, universal property of Quotient ring. Okay, let I be a two-side idea of R. Then we have a map phi, a map from R to S is a ring homomorphism, and I in the kernel phi. Then S is a unique ring. This phi tau is an R mod I to S. Okay. Now we have this map here. R to S is the phi. And then this is the projection map, just how we see. Okay, I send R to I plus R plus I. And then we have a unique here. So this formula we find equal to like B delta pi. Okay. Okay, then we prove this, which want to check the well defined and the homomorphism. Well defined is similar. And then skip this. But this we want to check two homomorphism. One is no, not two. One. Okay. The times is same. Okay. Because this is by definition, and then this we send to RS. But not send. The definition. Okay. Okay, so this phi tilde pi. Okay, then this right phi rs. This is rs plus I, the project. Okay, it's two. So yeah, we define like this. I don't write just now. Later I just.
I think on the first one, right? If it's defined, right, you write a dot equals.
Oh, okay, okay.
Yeah, otherwise we will regard that the future and this already are the same. So you should write definition.
Oh, okay.
Okay, then second is a well-defined. Although what is written is not wrong, but then you should show well-defined for your phi tilde. Right? So you should end up with phi tilde r plus I because phi tilde s plus I. Yeah, you should take that.
I already chose this.
So that's the problem.
Yeah,
So
okay,
that's
okay.
the problem. So that's what I tell you.
Okay.
So you shouldn't make them equal. They are like, I mean, like phi tilde. I don't know. I only know about phi. So you should dot equal. So that's what I say. So this the way of writing is confusing. Although the argument is okay, but then the writing is confusing. So in the end, you should show that, for example, homomorphism is also the same. You should end up with phi tilde r plus I times x plus I equals to phi tilde r plus I times phi tilde x plus I. Yeah, so you need to have extra step.
One more step less.
One or two more. But then, yeah, well defined is the same also. So you start with f phi tilde first, and then end up with phi tilde.
No. Okay. Next. Yeah. Next is the canonical decomposition. Every ring homomorphism phi we can decompose as like this. This is the subjective map, subjection map, and this is the inclusion map. And then we know this is the isomorph. And this map, the phi tilde is here. This is like same as I just before I said the group is very similar. I just we change to the ring of homomorphism only. Huh?
Even for set with I show it.
Yeah.
It's actually just set. Set don't have curl. Set don't have curl. Set. Oh, I mean, what? I know. Because the kernel asks everything set to identity and set and want to pick up an identity. Sorry. So we cannot have quotient set, right? No. We are not doing quotient set, but then we are quotienting elements that have same image. Yeah, we have equivalent class for elements that have the same image. So this is what the quotient includes. And those have same image, we send them to the center. So he is claiming that there's no kernel. I mean, like how to look at kernel, the general function of. But then in that case, we are looking at we are introducing equivalent class for elements that have the same image. So actually, you take quotient is what you're
just example Z to you quotient and Z you like 6 Z you take the 0, 6, 12 send to the send 0, right?
Yes. Yes. But then by doing that, you also have elements, have different elements that send to the same image. So we split them into versions of concept.
Okay, okay,
And
okay. Okay, thank you. We want to prove this is isomorphism. Then we want to prove the subjective and injective. Okay. Subjective is a very easy one because just R center R or for every here PR we have it R center. Okay, and injective because injective we prove another way. Before we prove like how to say phi A to the phi B, we want to prove A equal B, right? Now we prove using the kernel is 0, only one, okay, only one element. We want to prove the kernel only has one element, then the phi is injective. Okay, thank you. Okay, then we next is first isomorphism theorem. If this phi is a surjective ring homomorphism, then this R mod kernel phi is isomorphic to S. Because if this is surjective, just now, if this map is surjective, then this is equal to this. Okay, the image is equal to the S. Then this will isomorphic to image, and then this equal to S. Okay. Okay, next, the idea of a quotient ring. Okay, just now we have a quotient ring. Then we want to talk about what is the idea of the quotient ring. Okay, and the idea of the quotient ring R mod I correspond to the idea J of R such that I in J. Just see like this. If the J is between I and R, and then we take the modular R mod I is the J mod I is a idea of R mod I. You can see right here. And next is a third isomorphism theorem. Okay, I let I and J be an idea of R, and I contain in J. Then J quotient I is an idea of R quotient I, and we have this third isomorphism theorem. We also see before for the group. Now it's a ring only. Okay. Yeah. Check this. I'm going to prove this is isomorphic. We want to prove surjective, injective, and objective. Oh no, no need to prove that because just now we have the first isomorphism theorem. We just apply this on it. Okay. We want to prove this is subjective because what is this? This P actually a big phi. Okay. We let a big phi define a big phi is R mod I to R mod J, R plus I to R plus J, and then I write down the map. Right. Please. Let me check. Okay, like this map, and then first isomorphism. Yeah. Okay, if we want this, we know already this is isomorphic to image. Okay, then if this is subjective, you want to prove that after we prove, we can apply this is equal to like, so we have isomorphism to this. Okay. Okay, then why is subjective? Because the kernel of phi is r plus I, where the r plus j is j. Because kernel is same these two identity. Identity is 0 plus j. Okay, j. So by definition, this is j mod I, r plus I for all r in j. Okay. This is the injective. Subjective is very obvious because for every r here, we have this r sent to here. Okay, subjective. And then we have this isomorphism. This is to check the the kernel is j mod I. And this is check. Just take this to see. Okay. Okay. We had already finished the section 3. Then next we go through the section 4 is the idea and the quotient. No. Section 4 is the prime idea and the maximum idea. Okay. Okay, before we talk about the prime idea and maximum idea, we want to talk about what is the principal idea first. Right. Let R be a commutative ring. A commutative ring is
Why don't they define principles that from math and real life? Why suddenly change to motivating ring?
yeah.
Why suddenly they decide commutative ring is better?
I think like this because I think maybe you want to not specify the idea left right to choose the idea for all. So do the principal idea also you use the two side, right? I think it's like this lah.
Why not this time?
Huh?
Like previously, I don't see like where you just use left or right idea.
Yeah, just use two side.
Yeah. Yeah. So then why they not feel stuck not going forward? Maybe you read a bit.
Okay. Yeah. Okay.
Yeah. This case is the this case is the right idea.
Is it right?
This case is left side. Right is the thing that you multiply
Left or left? Left.
left.
Definitely left. Left. This idea, an R type idea. The principal idea is defined like this. We bracket A is for every R times A. In other words, principal idea is generated by an element. Okay. Okay, this is an example. The bracket 0 is only a 0 in the not inside of this for every string. And then the principal idea bracket I just is R itself because everything times 1 is in Z. This bracket n is mean nz. Okay, every multiple of n. Yeah. Okay. Oh, I want to check why this bracket A is an ideal. And then just now I say okay, same thing. Just a time the R T we also can Tx is also in A. We have this from same thing. Okay, we have the principal idea which is the idea generated by an element. Then we also have the idea generated by more than one element. Okay, we define like this the linear combination of the element. And this is an example, but okay, we haven't talked about this this square bracket. This is the polynomial ring. Yeah, okay. Later we talk, then we come back here. Yeah. Okay. Okay, next, we have idea, right? Then we want to think about how about the addition of the sum of idea also is idea or not? Okay. Okay. And then the proof is two things. One is we want to prove this group is a subgroup first. Okay. When to prove a subgroup is before we have the proposition say we just prove A B inverse in the set. Okay, is enough. Okay, so A B inverse here this is addition, right? Okay, sum the addition ing. So A B inverse A minus B lah. Okay, here is X minus Y. So you see this in. Then we check about after we check the subgroup, then we want to check this idea or not. Okay, idea mean we times something left or right. Okay, it's still in the idea. Okay. Okay, next is the intersection of idea is idea or not. Okay, same thing. Okay, same thing as the sum of idea, the proof. Yeah. The intersection is also idea. And then the product also is idea. Okay, or product of idea is also idea. And the proof is similar. Okay.
I think the
Oh, yeah. Okay.
otherwise it won't be a product, you just get the usual product set. That's generally it's not just algebra. Oh, because usually you write IJ just I from IJ on J, but then just maybe
Okay.
the sum of IJ.
Uh,
Usually you write I and J is just element from I and element from J. But then now you need the sum of them. Otherwise, no IJ.
If you just look at product of ij, then I'm likely I don't find ij.
So we'll just define the product idea of one. Product of idea is one.
Yeah.
Not idea.
No, I mean if you just take product of ij, then it won't be an ij.
Yeah.
You need to be generated by this.
Yeah, okay. Oh,
This notation，
啊
this notation，
把这个 abuse 是很正常。
哦，它的 generator，你的 generator，哦，明白。它的原告我们是 generate 的意思，
yeah，
是没有问题的。
对啊，没有问题啊。我只是想要point out这个。
is that?
啊
Is that?
if you just have ij, you cannot follow it.
That is the combination or IJ.
Some yeah, some need to consider that some.
The sum.
So the R here is competitive.
Yes.
Okay. Fine. 怎么让出下一个 case？我为他做模特。
Okay. And next, we talk about the product and intersection, the relation between these two. Okay. Okay. That IJ is the idea of R, then the product is contained in the intersection of IJ. Okay. We can easy to see why, because I intersect J is every IJ is in here, because every IJ, right? Every I times J is in here, also in here. Okay. So this intersection must be the big one. Okay. This is a small one. The proof is like this. These are example for the intersection and product, and then we will see why cannot be equal. Okay. Okay. This example is can equal because 4 and 3 is the 4 prime. Okay. But if you do the 4 intersects the 6 one, this is not equal prime. The LCM is 2, right? So it cannot be equal. Yeah. This must be bigger than this. And this contain the more element of the. And this example why is not equal. Okay, next we will talk about the polynomial ring. Say the polynomial ring like this, the notation is this R square bracket X, and then this contain all the polynomial. Okay, thanks. And then later we want to talk about the quotient. The quotient like we can think quotient like 55. Okay. You see there, you can have a bracket mean the idea generated by fx. Okay. So this quotient is defined like gx plus the idea generated by x such that gx is in the bracket. Okay, this is the quotient. Just later we see why we this is mean like fx equals 0. We have to solve. Okay, yeah, later we solve. Okay. First, we want to talk about the monic polynomial. The monic polynomial is just say the leading coefficient is 1 more. Okay, the big one, the highest degree terms is 1. coefficient. And this example, this highest degree term is 1, but this is not. Okay. Okay, next, this is a division by the monic polynomial. This is very easy, and that we want to use this thing. Every gx, right? If let fx have a monic of a degree d, then every gx we can write like this. There exists a qx and rx. Qx mean like the answer after you gx divide by fx. Okay, and then rx like the remainder. Okay, so we can write like this form. And then the degree of rx must less than d, less than this divisor. Okay, yes. This is degree d, so we want to less than this. Otherwise, we can do further factorization and then get less than d. Okay. And next is a proposition say the uniqueness of the remainder. Okay, if same polynomial I divide the fx, I have different the q and the r remainder, then this q and r must be equal. This q1 must be equal to q2, r1 must be equal to r2. Okay, because the degree. And this is a proof. I don't go through this. Okay. Represented in R square bracket mod the idea generated by F. Okay. Okay. Every of these elements, we have a unique representative from this x to the x to the power of d minus 1. If the f is degree d. Okay. Just like very easy one. I think like if f like square plus 1, if we can further factorize. Okay. Yeah, we can further factorize, and then this inside here is minus 3. Okay. Okay, so the degree must less than the 2. Yeah. And this is the proof. Okay, next is the proposition say let R be a commutative ring and A is in R, then we do a quotient here is similar to the R. Okay. Because we quotient the X, and then this is less than the degree 1. All of these like a number. Okay, a number is isomorphic to R. Okay. And this is a proof. Just we want to apply the first isomorphism theorem. Okay. Okay. So same now, I don't go through this. And this example for quotient the x squared plus 1. Just now I say. So why? So just now I say why we want to think about like this is fx equal to 0. Because like this. So you can think this is like we want to find the element, right? We just like gx is a big polynomial like f5 plus x4, 3x3 minus 47x2 blah blah blah. Okay, that's 1. Hey, we want to find the what's the element now? We just if 3 plus 1 idea generated is, then we just want to see the fx equal to 0, and then we have the x equal to plus minus I, right? We just apply the gi and g minus I, the high school, okay, the high school one. And then you can, okay, we can find the remainder, and the remainder is this inside this, okay, like this. Can I? Okay. The idea is like this. Okay. Okay. The proof for the example. Yeah. Okay. Now is a prime idea and a maximum idea. Okay, to define a prime idea is if I is a prime. First, we talk about I is not equal to R first, and then if I is prime, if R mod I is an integral domain. An integral domain is definition 之前的啊，那个应该是 Chapter 1 Chapter 2的 Section 1 Section 2的那个 integral domain， 但是他没有讲完嘛。OK， 哦，不，它这个是课本啊，this is a textbook, and then we have another equivalent to the some other two thing. And this is very hard to think. Next one is very easy one. Integral domain is mean if R is integral domain, then for every AB, every A and B in R, AB equal to 0 implies A equal to 0 or B equal to 0. Okay, can I integral domain? The quotient is different one. Quotient, if we talk about the quotient, is identity. Okay. And 0 plus I is identity. Then for the quotient. Okay, that is a maximum idea. If idea is a maximal, then the quotient R mod I is a field. Okay, the field is just the ring. We have the commutative multiplication. Okay, no. Inverse. We have inverse. I will have inverse. Equivalent condition is very easy to think because very hard to see. Okay, we say ring is a prime. Not ring. The idea is a prime. Then it's very easy. AB in I, then A is I or B. Yeah, just the same as integral domain mean. Once integral domain string. And then if a maximum idea. If a maximum idea is equivalent to like we say maximum, right? We want to see if this is a maximum idea or not. If this is not, I have a J is a maximum, but the J is either I or R, then I is a maximum. Okay. If the J is not equal to I or R, then it's inside here, then I is not a maximum. Okay, this is a very easy thing. And then the proof, just skip this now. And then it's I think it's where I think it's an important thing is we want to know the field is only have two, right? Because either you only have 0 or you is all because field is have inverse, right? If you have an element in the idea, you also have an inverse. Inverse time the element also in the idea, right? And then one in idea and everything is in idea. Okay. I think the more important is this. Okay, next talk about the relation between these two. The maxima is implies a prime, but the converse is not true. Right? Not always true. Might be true, but not always. Okay. So why like this? Because maxima idea, we say this if this ring this quotient is a field. Okay, if this is field, then every field is integral domain. Right. So if this is integral domain, then the I is also the prime idea. Okay. Okay, this example for prime idea may not be a maxima idea. Okay. In Z, the zero idea generated by zero is prime because it's very hard because this is only a zero, right? Everything times zero is zero inside the idea. Okay. You also can think like this: the quotient is a integral domain. Okay. Okay, but this is not maximum because we have the idea generated by 2. Okay, between these two, and this content is, and then this content inside the. Yeah. Next, we talk about what is the condition if the prime implies the maximum. Okay, and the condition is we let I be the idea of commutative ring. Then, if this is finite, the ring, the ring quotient mod I is finite, then we have the if why? Because if finite, you can think if the ring is finite, then
Simply prove
that's how. Oh, okay.
because after we prove that people ring finite,
Well, this very easy. I told now another ways to think now. Okay. Yeah. Also can. Also can. Okay. I think a finite. Finite is if an element in here, then some n go to the identity, right? Identity is I. Right, properly. Okay, the finite. Yeah. Then if it is identity, then we have the inverse. Okay, we have inverse R plus I term R plus n minus 1. Then this is inverse of this. Okay, if this inverse means this is the field. Okay, just like that idea. Okay, I'll also can you. Okay, the idea of Jack is very easy because everything multiple is idea. Is a prime idea. In Z, right? This prime, every idea is prime, and then also is a maximum. If the idea generated not is 0. Okay, if 0 is not wrong, right? Okay, just now we see already. If not 0, then the idea generated by n is prime, and same time is a maximum. Okay. Oh, have a one condition. N must be prime integer. Okay. You can think like this, because if you're not the prime, you can do the factor, right? If you're not a prime, you have 3 or you have 2. Okay, not a maximal. But if you is a prime, you cannot do the factor, right? So it's a prime. Okay. I can think like this.
Why, for example, z mod 6z is not an integral.
Oh, because the 3
3 times.
the idea generated by 3 is inside between the 6 and the integer. Maybe I can add inside.
No, I mean, you want to show that y6, right? Z mod 6, that is not an integral.
Oh, yeah.
Yeah.
Okay.
You just say that 6 is not prime, but then the idea would be that 6 is prime, but then 5.
Yeah. Because if you take mod 6z, this is not the integer domain, right? Because I have 2 elements, 6. And this time, this is 6, right? In the z mod 6 is equal to 0, right? Okay. So we cannot have this property. Nice. Not necessary. Sorry. This is 0. Okay. We can have the not zero number and then get a 0. Okay, next we talk about the spectrum. A spectrum is a set of all prime ideal. It contain all the set of all prime number. Okay, for example, like this, all prime. Spec Z. Okay. So,
希望自己还有球位。
这里啊，下次有机会有缘分的啦。
定义而发现的嘞。
Okay, next we talk about the PID, the principal ID domain. In the textbook, right, we call the PID is before. I put the last. Okay, I put the back because I think the PID is used for the after part. Okay, integer domain is called principal ideal domain if every idea is principal. Okay, like that, because every idea here, right, is every idea in Z is only you can write like idea generated by an element. This example, if you have 2 different elements, this is like 3k plus 6h, the combination, right? You also can write. I don't write. How to say it? Okay, example. Okay. The element you can write like 3 times some k. 3 times some number. This is equal to this. Okay. And every idea generated by the element you can write something like this. Okay, if this 2 element is a prime, co-prime, then this is what? Okay, Z itself. Yeah. So every element, every idea is in J is a prime principal idea. Okay. Okay. Generated by the GCD. Generated by a GCD of 3 and 5. Okay.
These are actually like related to number theory.
Yeah.
The integral solution to the pattern equation.
Sorry.
Integral solution for pattern equation.
You mean
X plus B1.
1 equal to 3x plus 5? Not 1. The GCD of a more general A, B, GCD of A. Okay. Yeah.
Also related to the Euclidean algorithm. To find the A, B. You want to find X, Y, you can use Euclidean algorithm.
Yeah. Okay. Okay. Then prime idea is PID. I'm going to put this. Okay, I propose to say R the PID, and let the I is not equal to the idea generated by 0 be an idea of R. Then if I is prime idea, if and only if it is also maximal. Okay. This is if the R is the PID. Okay. This condition. Otherwise, we cannot have this action. Okay. Because R is a PID, so the idea all idea is generated by an element, and then we just use before before thing. If we have a J here, right? We cannot, and the J is generated by an element B. Then this B either is I or it's B equal to A or B equal to 1 is R itself. Okay. Yeah. Okay. And this example lah. If just now we see already, this is a PID, and then if the prime idea is not a non-zero prime idea, then this also a maximum. Okay. But this polynomial ring, right, set as the Z, right? Very similar. If you generate by a polynomial is irreducible, okay, then you cannot have factorized, right? And so it's a maximum ideal. Okay, you can think like this. Okay. Example for the complex ring, polynomial ring. Every time that this 0 is not a maximum or means a prime. And why this mean? This mean like if a polynomial, the idea, the maximum is this x minus z for some z is c. Like example, every time we have square plus 1 x minus I x plus I. Okay, you can think like this. X minus z. And z is I lah. Then the spectrum of C complex ring polynomial is like this. Union. Spectrum is made the prime idea, right? Generated by one element like this. Every polynomial we can factorize this. Okay. Every yeah. Okay. Thank you. Thank you. Have problem or not?
How you define the idea and an idea in not configuring as the first event. Later, every session said that it's a configuration.
why I define the ring is commutative ring every time.
No, my question is why you define the idea in a non-commutative ring as the first, then later then you consider it.
At the first time, I want to let you know they have many version. Then later, I want to use the left right and not to say not to repeat. And then all thing is two sided. 很显那个
不懂
I mean 就是先给你知道有这样的东西啊，然后我过后用的东西都是要two sided。
不是通常人家要这样子的话，是因为有些情况只有 left，有些情况只有 right 会 exist，他们才会这样做。
啊，对，
他不会忽然间来制造一个没有用的东西，然后跟你讲这个东西没有用，然后不用用。他应该是在某个情况下有用。
哦，明白。
那书是这样做啊，我不懂啊，我还没有来真正读。
其实是都有用，只是
它应该是某一个 part
使用。
没有，它应该是某个 part 是 like 只 deal with left 或者只 deal with right 先来的。不然的话，它不会忽然间造一个，就看起来没有用的东西啊。
是有道理。我去看看了哦。
呀，可以啊。因为它可能会比较奇怪的 ring 啊，我不懂啊。non-commutative 啊，for example maybe matrix 里面哦，可能 matrix 里面的 idea 跟 left 跟 right idea 长不一样。
其实我有跳过一些 example 啊，所以可能会
maybe 那些
example 是用到
left right 不一样。
我没有 proposition 我没有跳啊。
对不对？
只是 example
这样也很奇怪，其实。如果就一点小 example 的话，就也没有什么很重要，除非来有一些 proposition 是 full commutative ring。
有道理。
对啊。
好，我先看一看。我看过有的 add 进去。
好。
我觉得这里面是
我觉得没有什么废话。我觉得没有什么废话，蛮扎实的内容。
已上锁，已解锁，请取出话筒。
也跟得上。Okay, very good. Maybe we can break around 5 to 10 minutes. The next one can ready. 谁是下一个 ？Okay. 猜一猜。
Sorry，
你有收到我给你的那个吗？他们的 feedback？
有。
有 ，OK。
我还没看到。
你还没有看？你还没有看？
I see。